Hello, I'm Aditi Vijayan and I recently finished my PhD at Indian Institute of Science. I want to discuss a recent work submitted by Milky and myself. This paper is titled X-ray spectra of circumgalactic medium around star-forming galaxies. The motivation for the paper is related to the way we interpret the observations of CGM. CGM around star-forming galaxies is in general multiphase. This is a result of interaction between the ambient gas and the supernovae ejecta. The hot phase of the CGM results in diffuse soft X-ray emission around the galaxy. The X-ray spectrum of this diffuse emission is a very important source of information for the hot gas temperature and metallicity. In order to interpret the spectrum and obtain physical quantities from it, fitting models are generally used. These models are based on some simplifying assumptions about the temperature distribution of the underlying plasma. The main question that we are asking is whether the popularly used spectral fitting models are representative of the gas distribution in the CGM. That is, are they physical? We have tried answering this question by analyzing 3D hydrodynamic simulations of a Milky Way mass star-forming galaxy. These simulations are discussed in the 2020 paper by Lee and Tonneson. At the beginning of the simulation, the gas is isothermal at 1 million K. Hot outflows from star formation overwrite this initial uniform temperature distribution. After a few gigayears of star formation, the mass distribution in temperature exists in a broad spread around a peak, which is the curve that you see. We use the simulation data, that is the density, temperature and metallicity information of the gas, as an input for PyXM. Using PyXM, we produce the spectrum between 0.5 and 2 keV. This spectrum that you see here has been binned at 1 eV, keeping in mind the spectral resolution of upcoming telescopes such as Athena, Lynx and Hubble. I want to point out that this spectrum has not been convolved with any instrument response. A popular spectral fitting model is the two-temperature model. As the name suggests, this model assumes that the X-ray emitting plasma comprises gas at two temperatures, T high and T low. Apart from the two temperatures, we also require the mass of the gas at the respective temperatures for complete description of the model. On the mass distribution curve, this model is visualized by two delta functions seen here as the two vertical blue lines. As previously, we can input the parameters from the 2T model into PyXM and obtain the spectrum predicted by this model. Through a method of hit and trial, we find the values for T high and T low for which the chi-square between the simulation spectra and the 2T model spectra is the lowest. The blue curve that you see in this slide corresponds to those best fit values of the 2T model. Though we find the temperature values that fit the spectrum, the mass distribution in this model is without any physical basis. To improve on the shortcoming of the 2T model, we propose a new spectral fitting model, that is, the log normal model. This model assumes that the mass distribution of the plasma follows a log normal in temperature. It is parameterized using a peak temperature and a width around a peak. Instead of an unphysical delta function, the gas has a broad distribution around a peak, seen as a magenta curve on top of the white curve from simulations. When we use a log normal model for spectrum, we find that it matches the simulation spectrum at both high and low energy ends. From our analysis, we find that the log normal model produces the lowest chi-square values. Apart from the comparisons I discussed here, we also discussed another popular fitting model, the one-temperature model in our paper. For the case of biconical outflows, we discussed the spectra inside and outside the bicones, and we showed the azimuthal dependence of the spectrum. And finally, by convolving the spectra with instrument responses, we provide mock observations for Chandra, Athena, Lynx and Hubble. The paper is now available on arXiv. You can reach out to either Mia or myself on Slack for any comments or questions. Thank you.